Welcome. Today what we're going to do is do some problems in first order linear differential equations. And so a lot of these problems that I'm going to do come out of a book called Schwamm's Outline Series, Differential Equations. Okay, so in section 6 of that text, I have the following question, which says to solve the differential equation y dash plus 3x squared y equals 0. Now this one is both separable and linear, but we should solve it as a linear ODE. And so what we need to do is first calculate the integrating factor and multiply by it. Okay, so the integrating factor here is I of x is the integral of this, e to the power of the integral of that with respect to x. And now to identify what to integrate, what you need to do is put the part with the single y over together on the same side of the equation with the y dash. Okay, and so we know that this is linear because a linear ODE is of the form y dash plus q of x, p of x, let's call it. We'll put the q of x on the other side. Y equals q of x. So this is a linear ODE. So p of x is a function of x and q of x is a function of x. And so the integrating factor is e to the power of the integral of p of x with respect to x. Okay, so that's what we're calculating here. It's incredibly easy to do this integral. So we've got e to the power of x cubed. Remember, we add 1 to the exponent and divide by the new exponent. And we don't need the plus c here because this will do the job. And that job is to multiply throughout by that integrating factor. So multiplying by I of x throughout the differential equation, we then have e to the x cubed y dash plus 3x squared e to the x cubed y is equal to 0 times e to the x cubed, so 0. Now the magic happens here because this always collapses down to the derivative of the product of y times the integrating factor. So always dy times I of x with respect to x is equal to, just using the product rule because this is how this works, I of x dy on dx plus the other way around, y di on dx, which we'll call I dash of x. Okay, so we always have that, and this is the p of x. Okay, and this is the thing we've multiplied by, this is the p of x times I of x. Okay, and so what we're doing is we're taking this, which is what we have here, and going the other way and packing this up into a derivative of a product. All right, and so what we have then is the derivative with respect to x of the product of e to the x cubed y. And so that's equal to the right-hand side. So we pack this up into this, and now we can just integrate both sides. So integrating both sides, we have e to the x cubed y is equal to the integral of 0 with respect to x, which of course is just a constant. Okay, and now we need to divide by that integrating factor. And so when we do, we have y as a function of x. Okay, so I write y as a function of x is equal to c times e to the minus x cubed. All right, and there is the problem done. So let's move on to another one like this. These will get progressively more difficult. All right, next one. Y dash plus 2 on x times y is equal to 0. Okay, so we need an integrating factor. Now, is this in the right form? We have our p of x on the left-hand side together with the y dash next to the y. Okay, so that's good. This is in a linear form. So p of x is equal to 2x to the minus 1. All right, now let's construct our integrating factor. I of x is e to the integral of 2x to the minus 1 with respect to x. Let's simplify that. So we have e to the power of 2 natural log of x. Now, I write log for natural log, but if you want to write ln, that's totally okay. All right, now we can simplify this because this is e to the power of log x, or natural log of x, all to the power of 2. E to the power of the natural log of x is just x, so our integrating factor is x squared. So what we want to do is multiply throughout by the integrating factor, so we have x squared y dash plus 2 on x, x squared, y is 0. So that this term here is 2 times x times y, but we know how the left-hand side packs up, right? It packs up as the derivative of our integrating factor, x squared times y. Okay, and if you want to check, you could just use the product rule on this. Okay, so let's say to check, use product rule. And so let's do that. We have x squared dy on dx plus y d on dx of x squared, which is x squared y dash plus 2x for this times y. Okay, so you can see it matches what we have here. So going in reverse, we get this. All right, now let's solve this. So integrating both sides, we have x squared y is the integral of 0 with respect to x, which is our constant. So now the general solution, y as a function of x, is c x to the minus 2, or c over x squared. Great. If you've got any questions, put them in the comments below. All right, next one. Y dash minus 7y is 14x. Okay, we need our integrating factor. This is in the correct form that shows that this is linear. Our p of x is minus 7 and our q of x is 14x. So the integrating factor is e to the power of the integral of minus 7 with respect to x, and this is e to the minus 7x. So we multiply by this, but we know how it packs up. It'll pack up as e to the minus 7x times y differentiated, and then on the right-hand side, we still have 14x e to the minus 7x. This is the integrating factor that we've multiplied by. Okay, so what remains is to integrate both sides and then divide by this e to the minus 7x. So we have e to the minus 7x times y equals the integral of 14x e to the minus 7x with respect to x. Now it looks like we need to use integration by parts here because we have a product of two things. And so to do that, what we need to do is transform this e to the minus 7x into a derivative. So let's do that. We have the integral of 14x. Now let's transform this into a derivative. I'll just put in a derivative and then I'll compensate. Okay, so what would happen if I differentiated e to the minus 7x? Well, I would need to use the chain rule, and that would bring out a minus 7 next to this, right? So to go the other way, I need to divide by that minus 7. So I'll just do that there. Okay, now check if this is right. Is this the same as this? Well, if I differentiated it, it would pull down the minus 7, it would cancel this, and we would end up with this. So that's fine. Okay, so let's continue. Now, this is a substitution, so what I can do next is get rid of the dx's and write this as minus 2 integral x with respect to e to the minus 7x. Okay, and so now I need to recall the integration by parts rule, which I often remember using the product rule of differentiation, which goes like this: duv on dx, but I don't need the dx here, v du plus u dv. Now if I took one of these over to the other side, I would have v du is duv minus u dv. Okay, so that's what I use here. Now we need to identify what is what, so here we have a v, and in here we have a u according to this. Okay, so now I can write this as minus 2 in brackets, the product of the u and the v, because we're going to integrate. So that's this piece. Okay, and so that's x e to the minus 7x, and then I subtract the other way around with an integral on it. Okay, there we go. So now this one is easy to do. So we have minus 2x e to the minus 7x, and then we have plus 2 for the product of minus 2 and minus 1. Now this integral is e to the minus 7x over minus 7. And now I need a plus c, because I'm done with the integration part of that. Okay, and so what we had, this was e to the minus 7x times y. Okay, so this is what we have so far. All right, so next what we need to do is multiply both sides by e to the 7x to cancel this and get a function of y. I mean a function of x as y. So let's do that. So y as a function of x is equal to minus 2x, because we can cancel this, and then we have minus 2 over 7, and then we have plus c times e to the 7x. Okay, and this is our general solution. All right, so that one was a little bit more tricky than the previous ones. Now let's go on and do another one. All right, y dash equals cos of x. Now this one's just incredibly easy. It's separable, right? So we can solve this as a separable equation just by integrating both sides. So we know that we've got so integral of 1 dy is the integral of cos x dx. That integral is very easy. It's just sine, equals sine x plus c. Okay, now this side is y. And so we have our general solution straight away. Now, can we do this as a linear equation? Well, let's write it in the correct form. So we'll say as a linear ODE, and this method is via the fact that it's separable. Separable, okay. As a linear ODE, we have y dash plus 0 times y is equal to cos of x. Okay, so the integrating factor here, so I of x is equal to e to the power of the integral of 0 with respect to x which is e to the power of a constant, or let's call it a. And so multiplying throughout there, we would just be multiplying throughout by a. And so the end result would be just this process right here. Okay, so there's not much to this when your p of x is 0. So let's move on and do a more involved question. I'll get a new page. Okay, next one, y dash plus 2xy equals 2x cubed, and now we're given an initial value y of 0 is 1. All right, so p of x is 2x, q of x is 2x cubed. So our integrating factor is e to the integral of 2x with respect to x, and so that's e to the power of x squared. And this is what we need to multiply by throughout. So we know how the left-hand side packs up. It packs up as the derivative of the product of this and y. And on the right-hand side, we have 2x cubed e to the x squared. Okay, and so now we integrate both sides. E to the x squared times y is the integral of 2x cubed e to the x squared dx. Now this looks like it would be just a substitution, but not quite, so not so fast. All right, so what you actually need to do here is do an integral by parts again. So let's transform this e to the x squared into a derivative. So derivative of e to the x squared. Now if we differentiated that, we would need the product rule, and that would pull down a 2x. So we need to compensate by dividing by that 2x. Okay, so this is the integral of x squared with respect to e to the x squared. All right, now let's write v du equals duv minus u dv. Okay, so here's our integration by parts formula. So what do we have here? Let's call this v, and this inside here, let's call that u. So we have the product x squared e to the x squared, subtract, and then we swap these around, e to the x squared dx squared. Okay, and now we can apply a substitution, transform that into this, and view this as a derivative right here. And so that becomes 2x e to the x squared dx. Okay, and now this one comes out via substitution because the derivative of x squared is 2x. And now we need a plus c. Okay, and so what was this? This is e to the x squared times y. And so what remains is to divide by e to the x squared, or multiply by e to the minus x squared. So we have y as a function of x is equal to x squared, because the e to the x squareds cancel, then minus 1, and then plus c e to the minus x squared. And this is our general solution. But we had an initial value, so that gives us an opportunity to find the value of c. So in this little piece of paper that we have at the bottom, let's do that. So we'll say, but y of 0 is 1. So what this says is that 1 is equal to 0 squared minus 1 plus c e to the power of 0. So we can take that minus 1 over to the left-hand side, and we get c is equal to 2. And then sub that in there, and that's our particular solution to the initial value problem presented here. Okay, let's move on and do another one. So in the next one, we've got dn on dt plus 1 on tn is equal to t, with n of 2 is equal to 8. Okay, integrating factor. This time the independent variable is t, and so our integrating factor is I of t equals e to the integral of t to the minus 1 dt. And so this is e to the natural log of t, and of course this is just t. So our integrating factor is t. Okay, great. So we need to multiply by that. So we have t dn on dt plus n is t squared. And we know how this left-hand side packs up. It packs up as the derivative with respect to t of the product of the integrating factor t times that dependent variable n. And on the right hand side we have t squared. Okay, now we need to integrate both sides. So we have t times n is the integral of t squared dt, which is 1/3 t cubed plus c. Now we divide both sides by t, and we have n as a function of t is equal to 1/3 t squared plus c over t. Okay, so that's our general solution. Now we want to use the initial value that we have. N of 2 is 8. And so we have 8 is equal to 1/3 of 2 squared, which is 4, plus c over 2. And we need to solve this for c. Okay, so c is equal to 2 times the difference, 8 minus 4/3. And now 8 minus 4/3 is 24 minus 4 is 20 all over 3. So 2 times 20 over 3, which is 40 over 3. Okay, now that we have c, we can sub it back in and write our particular solution to the initial value problem. And there we go. All right, now for the following question, it's an applied question about Newton's law of cooling. So it says a bar of iron, and when I write this, I'll just abbreviate it. So a bar of iron heated previously to 1200 degrees Celsius is cooled in a bath of water at a constant temperature. So let's write at ambient temperature. T subscript m is 50 degrees C. So the bar then cools by 200 degrees C in first minute. Okay, then the question is how much longer to cool a second 200 C. All right, so we start with the differential equation. Whoops, this is dt on d lowercase t equals minus k t minus the ambient temperature. So this is Newton's law of cooling here. And so we want to solve this differential equation. We already know that Tm is 50. Okay, so we can just put that in. So we have minus kt plus 50k. All right, now let's write this as a linear equation. In fact, you know what? It's simple to do this as a separable equation because it's also separable, but let's stick with the linear theme. So we'll write dt on dt plus k times t is equal to 50k. Now this equation is linear, it's in the correct form. So our integrating factor as a function of t is e to the integral of k with respect to t. So e to the kt. And this is what we multiply throughout by. Now we know what happens to the left-hand side. It packs up as the derivative of e to the kt times uppercase T with respect to t. And then the right-hand side, we've got this times this because we've multiplied throughout by that integrating factor. Okay, good. So now let's integrate both sides, and we'll get e to the kt times t is equal to the integral of 50k e to the kt dt. All right, now if we differentiated e to the kt, we would bring down an extra k. So going in reverse, we divide by a k, and so we get 50 e to the kt, and then plus some constant c. Okay, so now let's write uppercase t as a function of lowercase t. So we've got 50 plus c times e to the minus kt. And that makes sense because if you let enough time pass, this term becomes 0 and you end up with the ambient temperature. So that sounds sensible. All right, now let's use our initial values. So when t is 0, lowercase t is 0, so uppercase T of 0 is equal to 1200 C. So what this gives us then is the equation 1200 is equal to 50 plus C e to the minus k times 0. Okay, e to the power of 0 is 1, and so we have C is equal to 1200 minus 50. Which is 1150. Okay, fantastic. We're getting somewhere with this. So now we can write T as a function of lowercase t is equal to 50 plus 1150 e to the minus kt. Okay, and so what remains is to find that lowercase k. Now it says in the first minute the bar cools by 200 degrees Celsius. So what that means then is it cools to 1000. So this says T of 1 minute is equal to 1200 minus 200, which is 1000. Okay, and so then we have 1000 is 50 plus 1150 e to the minus k times 1. So this now gives us a way to solve for k. All right, so taking the 50 over to the left-hand side, we get 950. So 950, and then we can divide by the 1150, and we get e to the minus k. Okay, now let's invert both sides and divide by 10 on top and bottom. So we would get e to the k is equal to 115 on 95. Now let me reduce this fraction. So I'll just open up Mathematica here on the left. Obviously you can do it in your head. Okay, so that's 23 over 19. 23 over 19. And so that gives us k is equal to the natural log of 23 over 19. Now let's give an approximation for this. So write log 23.0 divide 19. I put in the 0.0 so I get a decimal approximation. And so that gives us 0.191055 and so on as our value of k. Okay, so we can sub that back into this and say t of t is 50 plus 1150 e to the minus 0.191055, etc. times t. Okay, so here's our solution. And now the last question was, how long does it take for the temperature to drop another 200 degrees? And so that would be to 800 degrees. So we need to solve 800 equals 50 plus 1150 e to the minus 0.191, etc. times t, 4t, lowercase t that is. Okay, so 800 minus 50 is 750. So 750 divided by 1150 is e to the minus 0.191 times t. Now let's invert both sides. So we would have 115 over 75 is e to the kt. And then now let's take the natural logarithm. And so we have t is equal to 1 over 0.191 natural log of 115 over 75. And now let's approximate that. You know what, I'll just call this k up here and put that in memory. Okay, and then I'll write 1 over k natural log 115 over 75. And so we would get 2.23728 minutes for the value of t. But the question, I think, said how much longer. So this would be 1.237 minutes more. Okay? Let's move on to another question. All right, the next one says, find the general solution. So we'll just say solve the ODE y dash is equal to 2xy over x squared minus y squared. Now notice this equation is homogeneous. Okay, because if we say let f of x and y be equal to 2xy over x squared minus y squared, then what we see is that f of sx sy is equal to 2 sx sy, so 2s squared xy over s squared x squared minus s squared y squared. And now if s is non-zero, we can cancel that, and we get 2xy over x squared minus y squared, which is the same as f of xy. So this fact means, since the two of these are equal for non-zero s, this means that the equation here is homogeneous, or the right-hand side function is homogeneous, and hence the differential equation is homogeneous. All right, so what that means then is that we can apply a special trick. So we'll let v be equal to y over x, and alternatively y is equal to vx. And so we use the formula dv over f of 1 comma v minus v equals the integral of x to the minus 1 dx. Okay, and this integral on the right hand side is easy. It's just natural log of x plus c. The one on the right is a little bit more tricky. So first let's evaluate what f of 1v is, or f1v minus v. So this is, looking at this, we've got, if we replace y with vx, then we've got, if we replace x with 1 in here, then we've got 2, and y with v, we've got 2v over 1 minus v squared for f of 1v, and then we have minus v. And so we want to put this over one denominator. So we multiply the v by 1 minus v squared, top and bottom. So we've got 2v minus v plus v cubed all over 1 minus v squared, which is equal to v plus v cubed all over 1 minus v squared. Okay, and so we come back up to this formula. This formula requires the multiplicative inverse of this. So we need to flip this. So inverting this one, we've got dv on f of 1 comma v subtract v is equal to the integral of 1 minus v squared over v plus v cubed dv. And so now we can break this up using partial fractions. So this factorizes as v times 1 plus v squared. And so we can break it up as dv over v minus 2 v 1 plus v squared, like this. All right, so if you need to brush up on partial fractions, do so, but I'll just tell you that this is how this breaks up. And so you can check it by cross-multiplying and checking that you do get this. All right, so now let's complete this. So the integral of 1 on v with respect to v is natural log of v. And notice that the derivative of 1 plus v squared is 2v. So we have derivative over the function. And so this is natural log of 1 plus v squared. Okay, we've already got our plus c on the other side of the equation right there. So we don't want to put a plus c here, because then we'd have too many of those. Now, we can use a log rule. We have a difference of two logs, so we have the log of the quotient. So log of v over 1 plus v squared. Okay, good. Now we're getting somewhere because this gives us a solution. I'll rewrite this. Log v over 1 plus v squared is equal to log of x and then plus c. All right, but v was y over x. So we'll keep that in mind. Okay, now we've got log of y over x and then 1 plus y squared over x squared is equal to log of x and then plus c. Let's multiply top and bottom of this fraction by x squared to simplify this a bit. So when we do that on the numerator, one of the x's cancel and we have x, y. Now on the denominator we have x squared plus y squared. And so that's log x plus c. Now I can do one more thing. I can take this over and use a log rule and call that the log of the quotient. Okay, but now we need to simplify this. So this gives us log of y over x squared plus y squared is equal to c. Okay, now let's solve this for the interior of this log. Y over x squared plus y squared is equal to e to the power of c, and let's call that a. Okay, and then finally, taking the x squared plus y squared over to the right hand side, or actually let's take that a over to the left hand side. So we'll have 1 on a times y is equal to x squared plus y squared. And then let's rename the 1 on a as b. And so we can write this solution as x squared plus y squared minus by equals 0. Or x squared plus y squared equals by. Okay, so there's our general solution to that homogeneous differential equation. Okay, next one, solve the initial value problem. With y of 1 equals minus 2. Now this one looks to be homogeneous also. So we'll say the ODE is homogeneous. So we'll let v equal to y over x, and we'll set up dv over f1v minus v is equal to the integral of x to the minus 1 dx, which is log of x plus c. Okay, so we need to calculate this for this f of x and y. So f of 1 comma v minus v is 1 plus v squared over v, subtract v, which gives us 1 plus v squared minus v squared all over v. So it looks like we get 1 over v for that. And so inverting that and putting it in here, we've got dv over f1 comma v minus v. This is the integral of v dv. So 1/2 v squared equals this, log of x plus c. Okay, let's multiply throughout by 2. So v squared is equal to y squared on x squared, which is 2 log of x plus twice c, but let's just call that b. Okay, and so we can now finish this off by saying y squared equals 2x squared natural log of x plus b x squared. Okay. All right, let's move on to the next one. Oh, no. I haven't done y of 1 is minus 2 yet. Okay, so y of 1 is minus 2. So we then have, so minus 2 squared is 4 equals 2 times 1 squared log of 1 plus b times 1 squared. Now e to the power of 0 is 1, so natural log of 1 is 0. So this says b is 4. And so what we get then is y squared equals 2x squared natural log of x plus 4x squared. All right, let's move on and do another one of these. Solve the initial value problem. Y dash equals x squared y minus y over y plus 1 with y of 3 equals minus 1. Okay, is this homogeneous? No, it's not. So not homogeneous. And you can see that because, well, f of sx, sy is not equal to f of x, comma y, okay? But you can also see that in the degrees. Now, it is separable, so let's separate that. So we can write dy on dx is y over y plus 1 multiplied by x squared minus 1. So I've just factorized the numerator and put the y's over there and the x's there. So now we can multiply by the inverse of this, take our dx over, and write this as y plus 1 over y. Dy is the integral of x squared minus 1 dx. So we can take this y into both terms of the numerator and call this the integral of 1 plus y to the minus 1 dy. And the right hand side is easy to integrate. We have a third x cubed minus x plus c. All right, now let's do the left hand side. We have y plus natural log of y is a third x cubed minus x plus c. Now let's use our initial value. But when we sub in a minus 1, we'll want to be a little bit careful, won't we? Okay. So let's rewrite this as log y 1/3 x cubed minus x minus y plus c. And so then solving this for this y, I know there's a y over here, what we would get is a e to the power of 1/3 x cubed minus x minus y. Okay, so here we have this. We've got y on both the left and the right hand side, but now it's possibly a little bit easier to see what to do with the initial value. Okay, so we've got minus 1 equals a e to the power of 27 over 3 is 9 minus 3 minus 1 is plus 1. And so in the exponent here we have 6 plus 1 is 7. So that says a is equal to minus e to the minus 7. Okay, and so then y equals e to the power of 1/3 x cubed minus x minus y minus 7, and then we'll leave that minus 1 out the front. Okay, there we have it. Next question. Find the general solution of x to the 4th plus 3x squared y squared plus y to the 4th over x cubed y. So this is homogeneous. And you can see that because the sum of the degrees here of this polynomial of x and y is always 4 in every term. Likewise down the bottom. And so f of s x sy will be equal to f of xy, where this is f of xy. So what we do is let v be equal to y over x. And so f of 1v minus v is 1 to the 4th plus 3 1 squared v squared plus v to the 4th over 1 cubed v, and then subtract v, and so this is equal to 1 plus 3v squared plus v to the 4th minus v squared all over v, which is 1 plus 2v squared plus v to the 4th all over v, which we can pack up into a perfect square in the numerator as 1 plus v squared all over v. Okay, and so the integral we need to calculate to solve this is the integral of 1 over f of 1v minus v, which is the integral of v over 1 plus v squared squared dv. Now, what we can do is set out a substitution. Let u be equal to 1 plus v squared. Okay, and so we want to differentiate u. So du on dv is 1 plus 2v. And so this tells us then how to... Oh no, it's just 2v, isn't it? There's no 1 there. So 2v, this tells us how to replace dv. So what we want to do in our integral is replace dv with du over 2v. Okay, so we do that here. So this becomes v over u squared, replacing dv with du over 2v. Now you can see what happens. The v's vanish. So we have the integral, or half the integral of u to the minus 2 du. So now we can add 1 to the exponent, divide by the new exponent. And so that gives us u to the minus 1 dividing by minus 1. We have minus a half in front. We'll leave out the plus c because that will go on the other side of the integral, as in here. We'll have our plus c in that. Okay, now let's put our u back in. So this is minus a half 1 over 1 plus v squared. and that's equal to the integral of x to the minus 1. So we have log of x plus c. And so now we have a relationship between v and x, but we know that v is y over x. So that gives us minus a half 1 over 1 plus y squared over x squared is equal to log of x plus c. And so we can multiply top and bottom of this fraction by x squared and get x squared over x squared plus y squared. Multiply both sides by minus 2. And then minus 2 times c, let's call that b. Okay, so now we've got a curve. And that's probably good enough as a solution of that problem. All right, let's move on to another one. So this one says, show that the integral of cos squared x dx is equal to a half x plus a quarter sine of 2x plus c. Okay, so to do this one, what we'll need to use is the trig identity or angle addition formula. So using the angle addition formula, that cos squared of x is 1/2 of cos of 2x and then plus 1. So we can replace cos squared okay, and now this is easier to do. We can break this integral up. Okay, and now letting u be equal to 2x. So let's do that. Let u be equal to 2x. Take derivatives. Du on dx is 2, and so then you can replace dx with du over 2 in this integral. Okay, back to this integral. This integral is easy. We just have a half x. And then here we've got plus 1/2 integral of cos of a u du over 2, having replaced that dx with du over 2 in a substitution. So a half x plus a quarter, the integral of cos u with respect to u, which is minus sine. Or no, it's plus sine, isn't it? It's plus sine of u, but u is 2x. And then we have our plus c. Okay, so we've got exactly what we're supposed to get there. Fantastic, let's move on. Okay, next problem. Calculate integral of x to the power of 5 times the square root of 1 plus x squared dx by substitution. Okay, so to do this, we want to let u be equal to 1 plus x squared and take du on dx. We get 2x. That tells us how to replace dx. In the integral. So we've got x to the 5th, u to the half, replacing dx with du over 2x. Now that gives us integral, or half the integral of x to the fourth u to the 1/2 du. Okay, now let's apply a trick here, because what we see is that u minus 1 is x squared, so x to the fourth is the square of this, u minus 1 squared. So we've got the integral, or half the integral of u minus 1 squared u to the half du. And now this is a polynomial times u to the half, so we can expand that and have a sum of u to the power of p, where p is possibly a fraction. Okay, so expanding this, we have 1/2 u to the power of 2 plus another half is 5 over 2. And then we've got minus 2 of the middle term. So we'll get minus u to the 3 over 2. And then we'll have plus 1 times u to the half. So bringing the half back in, half u to the half, and then du. Okay, now finishing this off, adding 1 to the exponent. So we have u to the power of 7 over 2, divide by the new exponent, and we've got 5 over 4. Or so, no, not 5 over 5 over, no, 2. We don't have 5 over 4. We've got 2's canceling, so we've got 1 over 7, don't we? Yes, 1 over 7. Okay, now for this one, adding 1 to the exponent, we've got u to the 5 over 2, divide by the new exponent, we've got 2/5. Yes, okay, and then adding 1 to this exponent, we have u to the 3/2. Dividing 1/2 by 2/3 gives us 1/3. Okay, and then we have a plus c. Now, u was 1 plus x squared. So our integral is 1/7 1 plus x squared to the power of 7 over 2 minus 2/5 1 plus x squared to the power of 5 over 2 plus 1/3 1 plus x squared to the power of 3 over 2, and then plus c. Whew. Okay, good. Next one, calculate integral of x squared cos of x by parts. Okay, so what we want to do here is replace the cos of x with a derivative. So cos of x is the derivative of sine of x. And so we can write this x squared d sine of x. And then let's say this one's u and this one is v. And so we then get x squared sine of x minus the integral of the other way around. So which is sine x dx squared. And now we can introduce a substitution and think of this as a derivative. So this is x squared sine of x minus the integral of 2x sine x dx. Okay, so next we want to be able to simplify this integral. So we must calculate integral of x sine x dx. So let's apply the same trick. We'll replace that sine of x with a derivative. It's the derivative of minus cos, but we'll say d cos of x on dx. Put a minus out the front. Okay, so now is this true? The derivative of cos of x is minus sine of x. It cancels that minus, and we get this. Okay, great. So this is minus integral of x d cos x. Now, if this is our u and this is our v, we know what to do. We have minus the product, and then minus minus, because there are two minuses, so that's plus the integral of cos of x dx. Okay, so we have minus x cos x plus the integral of cos x is sine x, and now we need a plus c. Okay, so subbing this, which is this, into here, we need to multiply this result by minus 2. So the integral of x squared cos of x with respect to x is equal to minus 2 times this, so and we still have the x squared sine x, so x squared sine x plus 2x cos x minus 2 sine x, and then plus another c. I'll just call this b. Alright, just to double check, let me open up Mathematica and get Mathematica to calculate that integral, because it was a rather tricky one. So I'll just say integrate, but there's a button that looks like an integral for this. So integrate, what are we integrating? X squared times cos of x with respect to x. Okay, so Mathematica gives x squared minus 2 times sine of x, so we can factorize the sine of x out of this to make it look like that. And then plus 2x cos of x, and Mathematica has not put down the constant of integration there, but we should. Okay, there we go. Now I need a little bit more paper to keep going, because there's a lot here. Okay, next problem. Calculate integral of, let me see, x over x squared minus 5x plus 6 with respect to x. So this one requires partial fractions, and I'll show you how to do that. But the first observation you want to make is that that denominator factorizes easily. Okay, so let's just say x squared minus 5x plus 6 factorizes as x with 2, x with 3, 6 is 2 times 3, and the sum of those is 5. So I want minus on both of these so that the sum gives me minus 5x. Okay, and so now what I want to do is say x over x minus 2, x minus 3 is equal to a over x minus 2 plus b over x minus 3. And I've got to work out what the a and the b are. Alright, so we multiply left one on top and bottom by x minus 3. So we have a outside of x minus 3 and then plus b outside of x minus 2, and that's all over x minus 2, x minus 3. Okay, so to do this, now I can expand and collect like terms and then solve for a and b in a system of simultaneous linear equations, but I don't want to because there's an easier way to do this. And so we say when x is equal to 3, right, because we want this to be, we want that numerator to be equal to x, or 1 times x. So we have this vanishing, and we choose this so that that vanishes. So we have 0 plus 1 times b, or b, is equal to 3x. Or sorry, equal to 3, because I've subbed in 3 for the x. And so that gives b is equal to 3. Okay, now let's choose the other term so that that vanishes. So when x is equal to 2, this vanishes, and we have 2 minus 3 is minus 1, so minus a is equal to x is 2, so 2, and that gives you a is equal to minus 2. Okay, so this tells us that the integral of x over x squared minus 5x plus 6 is equal to the integral of minus 2 over x minus 2, and then we have plus the integral of 3 over x minus 3. And now these two integrals are easy. We'll pull the minus 2 out in front, and we'll say this is minus 2 natural log of x minus 2, and then we have plus 3 natural log of x minus 3 plus some constant of integration. Now we can tidy this up a little bit. We can pack the 2 up into here and the 3 up into here and say that this is log of the quotient x minus 3 cubed over x minus 2 squared. Okay,